being overseas this week, has decided that I get to pretend to be him for a day. So, I don't know how much he's told you about me. My name's Julian. I am a founder of a company called Fpga Devices. And we're one of the few companies in Australia that does integrated circuit design. So given that you guys are all learning about digital circuits, if I'm understanding correctly, I thought I'd give you a little bit of an industry perspective on the kind of real digital design that happens in the part of the world that I look at. So I might as well start by telling you about the pretty picture. So this is a chip that we're working on in Brazil at the moment. It's being manufactured in a 65 nanometer technology. And this is somewhat typical of what a modern chip looks like. All of this yellow and purple stuff that you can see represents metal routing over a big array of digital gates. So this chip has 1.5 million gates of logic. And some of you, I'm sure, have been doing a few little projects which might consist of a few hundred or perhaps 1,000 gates of logic. So you can see there's a lot of work in that part of it. But there's also this little grey block. Oh, can't stand there. Is an analog to digital converter. I think it's actually two. And down here we've got a USB interface, because this is a digital set-top box for a specific standard, but of course the Brazilians want to do it different from everybody else. So
is this what set-top box are you saying?
Say again?
Is this for a high definition or standard definition set-top box?
No idea. But our role in this was to put together the whole chip. The customer had their code, which they said, oh yeah, it works perfectly, we got it in an Fpga, which isn't the whole story, sorry. So we turned their Verilog code into an array of logic gates, plus the integration work to connect to the pads around the outside, since that is only 4.2 by 3.8 millimeters. So you can imagine trying to deal with a pad over here which is maybe 80 microns wide is a little more difficult. Does anybody leave pens in this room? A pen that works on this? There's a piece of chalk, so I'm going to have to use that one. Oh, I've got a chalk now. So, the way I see it, there's three types of digital design that are used in the real world. You guys have been exposed to the first, which is the Fpga. Smart move. So have you guys have already started playing with Verilog and Fpgas, or is that something still to come? Okay, the second is big ASICs like that. And both of those we're using Verilog. maybe Vhdl. And the third is custom. And you'll all have started with a bit of custom design, actually working with schematics, drawing gates. Now, these fit on a continuum. I'm getting humming, it doesn't matter where I stand anymore. So, this is low cost in low volume. So the cost to design one circuit in an Fpga is the cost of one Fpga chip, somewhere between $5 and $100 depending on how expensive you want to make it. And you'll have a fair idea of the tools you use, the amount of work it takes to get it doesn't want me to talk to you. Does this happen for Nonny?
No, because he's always on that side.
He's always on this side.
He's always is. Now that I think about it, he's sitting down. He sort of wanders back and forth, but it's always in front of him.
It's never this far.
It's not there at all.
Oh, maybe I'll have... Okay, so one of them. I'll swap sides. Maybe it'll work over here. So this was low cost. It doesn't like me. Well, maybe I should. I'll just yell at you, that's much easier. So, an Fpga, is anybody actually listening to me, or are you all talking amongst yourselves? That worked. Yeah, and these front people as well. So, FPGAs are low cost when you only want to have a few, maybe up to a couple of thousand kind of things, because the cost of manufacturing is cheap because somebody like a Xilinx or an Altera is making them by the truckload. Your major cost actually turns out to be the engineering time in order to actually get the design to work for you. If you've got an ASIC, that's high cost, but it works in large volume. To move into production for something like that is going to cost somebody maybe $5 million. But then the chip comes out at something that size, maybe $1 a piece. So if you make 1 million of them, then the price is going down to $6 a piece. If you make 2 million of them, we're about $4 a piece. And at that point, we're cheaper than a $5 Fpga. So chips work in large volume. You think about the things you know that use a lot of chips. Intel microprocessors, lots of those. Apple iPhone has a custom processor in it. There's a lot of those. Those kind of applications, they're going to sell lots. The other place you're going to see is custom, and as I said over there, I did say over there, anyway, high speed. And this is going to be specialist applications. So if you want a specific piece of logic to run at 5 or 6 gigahertz, then the automatic tools writing a bit of Verilog and hoping the simulator and the place and route tool is going to get it right, forget it, it's not going to work. So there are a lot of applications, specifically in some of the high-speed communication standards. So you may know that, so inside your PC there's a lot of serial buses. The PCI Express is, depending on which version people are using, a 3 or a 6 gigabit per second serial link. Your hard drive is connected to the computer via SATA interface, which is again running at either 3 or 6, or maybe people are thinking about 12 now. But that says some part of your chip, or somebody's chip, in that system has to get the data from the sort of 300 megahertz you might get here up to the 10 gigahertz. And that takes a specific engineer doing the hard work and knowing what the transistors look like. This FPGA you might run in 50 to 100 megahertz. So in Australia you want a job, then this is where people will live. Because there aren't many. If you want these pieces to happen, then this is going to be the US or Europe maybe. So if you want to get a job overseas, you can think seriously about that. Otherwise you're going to have to be really good in order to convince some company overseas that you're worth living in a different time zone from the rest of them. And this one is just so small that unless you want to come work for me, you're not likely to find that job. So in that context, it's good what you're working in. You're working with the industry standard flow. This is where the people who are interested in what you do are going to do. So you're a bit of a big group, but probably only a few of you are vocal. So what I want to know is, are there anything that people want to know about? Anything in terms of either digital design or how it fits into industry? Because I've got some other stuff I can talk about, but if people have questions, then that can be much more exciting. Yeah?
So would your company use like Linux, or do you use your own software?
Well, we sit in these two spaces. So I have used a little bit of FPGAs, but mainly I'd use an FPGA as a convenient tool to test another chip.
So again, is Verilog the sort of standard way of communicating what you want out of the chip?
Yeah, so this both of these are Verilog. There's another language called Vhdl, which is used by some companies in Europe, which you had enough experience that if you went and looked at a piece of Vhdl code, you could puzzle it out. It's close enough. You'd spend a bit of time before you could think enough of that to actually be able to write it, but you could probably puzzle it out. And this last one's schematics. So the Verilog that you guys have been writing is exactly the same tools. Here you're using the Xilinx tools, so I don't know what format you got them. Presumably you all downloaded them from somewhere or other and installed them all on your own PCs. This one, there's a more complicated tool flow. You're not going to find that in the uni very often, because if I went out and I need that tool, it costs me about $1 million per year per seat. So, but that's the final. So, that looks like a chalk marker. So, I'll talk a bit about the flow. Because at the beginning, we've got an idea. We work out what it is that we want to build. Somebody has come up with a specification, marketing has gone off and decided what they think they can sell. And down the bottom, we have a product. Now, if we split it and do the Fpga versus an ASIC. So the Fpga is a relatively easy path compared to the ASIC. So you write your Verilog. You actually do the same over here. So the first step is much the same. You're going to write, you're going to debug. I don't know how much you guys have been using the simulation tools that Xilinx may provide, or whether you've just been doing a lot of putting it on FPGA and seeing if it works. Those of us who live in the ASIC world think FPGA design is just shove it on the FPGA and see if it works, and if it works then great. If it doesn't, then try again. Very much the same as software, guys. That on the software side, you can compile it, you run it on your PC, you can see if it works, and you just can keep cycling around. FPGA takes a little bit longer, maybe 5 minutes instead of 2. When you're paying maybe $100,000 to have a prototype made, you don't do that every day. So here we do a little simulation. Here we do a lot of simulation. And then you can compile and send to the hardware. So I take it you guys have all used the tool and have at least programmed one FPGA with something at this stage. And to a large extent, you press the button, you wait, and it tells you it's ready to go. If you look at the log messages in that thing, it's actually going through a number of different steps that probably normally wouldn't have talked about because it's not important to the... So it starts off, it takes your Verilog code and it translates it into gates. So it works out this is a structure of gates, or the LUT elements that they use in, which is like a reprogrammable gate that they use inside an FPGA. It'll work out how many of those and how to hook them up. Once it's worked out that, it does the next step, which is to say, okay, I have this piece of FPGA, and I know that on it there are a number of those LUT elements. It then works out which ones of those connect to what and how they're configured. So somewhere it's got to work out which specific pieces of hardware it's going to use, and then it finally translates that into the code that gets sent off into the Fpga that makes all that happen. So we've got that three-step process, and you just press one button and it all happens. In the ASIC, it gets a little more complicated. So we're going to start, after our sims, we do our synthesis, which ends up with our gates. So when you, I think actually you may have three buttons. You can do just a synthesis step on the Xilinx tool. But we're translating our Verilog code into the equivalent of a schematic so that we can then place it. The next step we're going to do is our place and route. So we've got our array of things here, and we're going to work out which gates go where, which ones I want to use, and get an idea of how they're going to connect up. So these two steps are much the same in these two. The one where it gets more complicated on an actual ASIC is we've got to start thinking about timing. So if we're running off, say, a 300 megahertz clock, are people talking again? Then each step, each operation, so you've got one set of registers clocked on one cycle, it does an operation, it gets clocked onto the next set of registers on the next clock cycle. So for start with a gate takes a finite amount of time to do an operation. So it doesn't just instantly, that's the solution, it takes a bit of time. We've also, particularly here, if I've got some nice little local interconnect, I could have some things that are just connected over here, but I might have something that's connected all the way up to the far corner of the chip. That's going to give me a big long wire, which has a lot of parasitic capacitance. So the timing, we're worried about how many gates can we fit in a clock cycle, how big capacitance is between them, and what size of the gates. So you can have different gates with different drive strengths. So it can drive a certain amount of current, or it can drive twice, 4 times, 8 times the amount of current, and you can use the bigger ones on the longer wires. Hopefully you can bring the timing in together. You get a little bit of this over here, but most of that's taken care of for you. And sometimes the only solution at this is to actually go all the way back up there and rewrite your Verilog code so that it takes more clock cycles, stores it in registers more frequently. So you spend a lot of time around here. Then we're finally and here we're going to finally generate the layout. So the ASIC also gives you a lot more flexibility. You have the ability to create as many transistors as will fit on your specific piece of silicon. We then take that one, we take away a level of abstraction or complexity by then choosing to use a specific number of gates. So we'll have an AND gate, OR gates, flip-flops, maybe 200 or 300 elements in a library available to us to use, so that we don't have to redesign an AND gate every time we want to use one. Whereas in the Fpga, it's all done. That bit's taken care of before you even start. But the manufacturing process means that in our individual ASIC we're going to be placing the transistors, we're going to be doing several layers of metal interconnect. Does it say how many? That one doesn't say, but it's probably got about 8 to 10 metal layers, so various different interconnects that, so that we can hook the various gates together, because if there's 1.5 million gates, there's probably something more than 3 million different connections that are happening over there. So we've got a generated layout, we finally send it off to fab, and we get a chip after, say, 3 months. So the other part of the reason that you don't make a new chip every day is it probably takes you about 3 months to get it back. Does that make sense? Any questions there? Yep.
Is the primary cost labour at this point, like people?
Okay, up to this point, labour and the software, because you probably pay about the same for the software as you pay for the people up to this point. Maybe a little more for the people, but the thing here is it's about volume. The number of people actually making ASICs like that, there's not a great deal of companies in the world doing that. So there's a couple of companies that sell the tools, and with an Fpga they're giving it away to you effectively because there may be 1 million users in the world. They can, but if you only got like 1,000 companies paying for all the development tools, they got to pay their share. At this point, now we send it off to manufacturing. Now what you paid here may or may not, but I guess it depends on the size of the project. This one we spent more on labour, and you can make a chip 10 times that size and the manufacturing costs the same to get started. But that's a 65 nanometer process, and you're probably paying about $500,000 for the tooling to make your specific chip, the mask set that has all the patterns for what goes where. If you want to get aggressive and move down to 28 nanometer, which is the latest generation of technology just going into production right now, then $2 to $3 million gets you your tooling. So if you don't have a market with huge amounts, then you'd better have a market that's willing to pay $100,000 a chip. And both markets do exist. Generally the second one belongs in the military. Any more questions on that?
You're saying that the digital design industry in Australia is big or?
Small. But in terms of ASIC, I can think of maybe 4 companies in Australia that would do any amount of ASIC work, and 2 of those would be more focused on analog. So in Sydney we've got Broadcom, which took over last year a company called G2 Microsystems, which do they were trying to do a sort of specialized low-cost Wi-Fi chip into sort of tracking applications. A chip that would listen to the GPS, work out where it is, and as it goes past the appropriate Wi-Fi, would tell the system where it's been so that people can track pallets and the like. There's a company in Adelaide, ASTC, that do a fair amount of this. They'll do these same kind of things, but they're the only company in Australia that really is focused on big digital chips. The rest of us are mainly focused on some analog or RF component, and we'll do a bit of digital on the side. Yep.
Just on the subject about the digital industry, how much has the digital industry embraced in NCL programming?
NCL is...
It's relatively new though.
It's new. So academics have been talking about asynchronous logic of various types for a very long time. But there is, I can take the blame because I got Noni started on NCL. Yeah. So it was his idea to give you an assignment on it, but
you told me to do NCL. Because our assignment's based on NCL.
Yeah, I know, he's told me all about it. I got him started on doing some NCL because I could see that it was really going to help him with his PhD. And then he said, if I've got this pain, then you guys can have it too. But there is a movement in the industry towards a lot of thinking about trying to make asynchronous logic work. Because you'll all have seen the clocked. Now, if we take a chip like this again, we go back. The thing you don't see from the layout is the power. Half of the power that a chip like that consumes is in the clock tree. Just getting a clock to the gates so that it works and making sure that the clock is consistent in timing across the whole chip. Because you can do a simpler clocking tree and use a quarter of the power, but then don't try and send a signal from here or back again, because the clocks are going to be at different times.
That's what exact. That's what you.
Yeah. So you need maybe to within like 5% of the clock period, you want the clock to be the same. Because back to this timing thing, any inaccuracy in that clock, you've essentially got to subtract it off your clock cycle. Because I'm sending something from here to here, and if there's an error due to that, then that edge might be here. And if I want it to work every time, then my logic can't take more than that.
So you don't want to try to minimize the delay propagation.
Yeah, so the net result is we've got the fastest signal on the chip is the clock, because any data signal that's being clocked by that clock can only run at half the speed of the clock, right? Every rising edge you write in your code, let the signal change. So, and the amount of power you dissipate is proportional to the number of times you go up and down. So the clock is running at twice the speed, it's going absolutely everywhere, and it's got the largest load because it goes to every flip-flop on the chip. So people are thinking a lot about NCL and other types of asynchronous logic at the moment because that clock power goes away. But yes, you've got to build your extra logic which sends your completion signal back, but you have some advantages. One, that's a local signal. It doesn't go very far. You don't have to buffer it up across the whole chip. Two, asynchronous logic naturally turns itself off when there's nothing to do.
Just follows the input pretty much.
Yeah. If you don't have an input, then if there's no new input, the NCL doesn't start again. Yeah?
So, with asynchronous logic, it seems that there's a lot of thinking about trying to do it. It's like, how much has it actually made it into graphical application?
So,
And what are the barriers to its, like, wide scale?
okay, the biggest barrier is as you're discovering it, it's difficult to learn to do it. And to a large extent, that's because the whole industry has been trained to think one way. Or maybe if we have a generation of people who come through and learn it at the beginning like you are, then once you pass that initial barrier, it's like it's no big deal. I do know that there is, certainly ARM is a company that I've heard of. ARM probably makes more microprocessors than anybody else because they'll be in every phone. There might be a dozen in your car, in your iPod, in any other bit of consumer electronics, there's at least one ARM processor in there 99% of the time. Now ARM, some of their products definitely have asynchronous logic portions of them. For that very reason, there are specific parts of it where they want to save power. So I think a number of ARM processors consist of a clocked outside that then translates the clock signal into the asynchronous signal, does all its work asynchronously, and then translate it back onto something that can be clocked, because everybody else is doing clock logic. So probably the most difficult part of that microprocessor is the translation between one and the other. And so there are a lot of companies like that who are thinking about, I don't know that they're using NCL specifically, but they're certainly looking at how can I deal with eliminating this clock or making it more local and saving that power.
So what is the dominant technology in the chips manufacturer recently? I mean, the synchronized circuit or...
So synchronized is very dominant.
Okay.
The question is more not what do we do now,
Yeah.
but what are we going to be doing in 10 years' time?
Okay.
So I'd say 99% of logic design, if not more, today is synchronous. 10 years' time, there might be 10% asynchronous,
Yeah.
and 10 years after that, who knows?
Okay. So what's your opinion towards the asynchronized circuit? Is it promising areas?
I think it's a very promising way because power is becoming more and more of an issue every year. And if you look at the big places that there's huge growth at the moment, you think about iPods, phones, portable devices, anything that uses a battery. Any time on a battery device you can use less power, that's a longer life for a smaller battery and your users are happier. So I think asynchronous logic is something that is coming close to having its day. Any more questions on that?
What are some examples of like the type of problems that you're dealing with, I guess, like?
Okay, so I have a little presentation about percepture. It's going to take about another half hour. Does everybody want like a 5-minute break now and then come back to that? Okay, 5 minutes.